All right, steady as she goes. Status report. The quantum quantifier measured a quantity of quantum energy beneath a quanta of quantum energy. In English, Quinn! Captain, I share your quandary. Quality quantum quantification of this quantity is quite quizzical. If you have no qualms, I request we quietly queue at this quintessential position and quickly quibble with HQ about this queer question. If that's a request to call this in, that's approved. I'll be in my quarters if you need me. Everything is connected. To learn anything, you have to build on what you already know. Whether it's science, art, or philosophy, we can connect everything to anything. So let's learn anything. Let's find those connections and let's build our intuition. Welcome to Intuition. My name is Evan Noche, and welcome to the beginning of the end. If you stuck with me this far, you've touched subjects ranging from metaphysics to physics and ethics to engines, and this hasn't been accidental. My goal for this project has been to not only bring interesting and varied topics to the table, but to then be able to break down and digest harder concepts by relying on those previous topics. Each of the 9 previous episodes has been building towards this one episode. This one topic that's eked its way into a lot of different episodes. That's right, it's time to talk about quantum physics. Which I think I may have mentioned before. It relies on electrons. Let's just dictated by quantum physics. Which is not beyond the scope of this episode. Much like our lesson on relativity, quantum physics is not observable on the scale we find ourselves in. And while relativity looked at objects with large mass or large velocity, we will instead go small. Very small. Smaller than atoms. Now, it's hard to isolate exactly who had the first thought of quantum physics, as it started out as a collection of observations that break conventional physics. Observations that scientists were so desperate to disprove that they came up with thought experiments, physical experiments, an entire mathematical system just to make sure it wasn't true. But the result was the same. Classical physics breaks down at small scales. I'll start with 2 scientists who each observed a strange occurrence with electromagnetic radiation, Max Planck and Albert Einstein. Max Planck struggled with the problems of thermodynamics and entropy. His new approach became known as Planck's law and solved the problem of the ultraviolet catastrophe. Let me back up a bit. If you remember from our lesson on radiation, objects emit electromagnetic radiation due to thermal agitation, which just means the molecules of an object are always moving. The issue was that objects ideally emit radiation at all wavelengths, and as the wavelength gets small, very small, the energy associated with that wave would be very high. And as the wavelength gets closer and closer to zero, the energy emitted would almost be infinite. This was a big problem, and Planck gave the solution. Electromagnetic radiation could only be emitted at discrete energy levels, multiples of an elementary energy unit. Now, what does that mean? Well, it would mean that objects could only emit at a specific set of frequencies because the energy carried by any electromagnetic radiation has to be multiples of a singular unit of energy. That would be like saying a battery can only have energy values in multiples of 2. So 2, 4, 6, and 8, and so on, and can't have values of 3, 2.2, or 1. That's a bit out there, but experiments proved that Planck's law worked. So that's strange. So what about Einstein? What was his observation? At the same time he was working on special relativity, Einstein published a paper on what's known as the photoelectric effect. Again, if you remember from the radiation lesson, high energy radiation can ionize atoms or strip them of their electrons. Einstein studied the phenomena of how electrons would be emitted from a metal plate when high energy light was shown on the plate. The strange thing he noticed was that there was a minimum energy required to eject the electron from the atom. Any light below this threshold couldn't remove any electrons. That would be like if you were playing pool and the cue ball simply didn't move if you didn't hit it hard enough. Einstein theorized that electromagnetic radiation could be thought of not as a wave, but as a stream of energy packets known as photons. Packets that had discrete energy levels. Sound familiar? Putting these together, both Planck and Einstein rationalized the light phenomena they saw by saying its energy is restricted to a specific set of values, each the multiple of some basic unit of energy, some basic quantity of energy. The quantum in quantum physics comes from the fact that at small scales, things are restricted to specific quanta of energy. But that's just light, right? Light is already a strange thing, so we're just adding strangeness to strangeness. But matter still acts normally, right? No, we aren't that lucky. The French physicist de Broglie was inspired by Einstein's papers on special relativity and the photoelectric effect that he based his entire PhD thesis on a similar topic. He theorized that if light can be a packet or particle-like and a wave, then electrons can have wave-like properties as well. You may remember from our first lesson on chemistry that electrons were definitely not described as light. They had mass and size. So how can matter have wave-like properties? De Broglie combined special relativity with the photoelectric effect to determine that if electrons had wave-like properties, they would have a wavelength based on that minimum quantum of energy and the particle's mass and velocity. theory is all fine and good, but now we've got to prove it. Enter the double slit experiment. If you are familiar at all with quantum physics, you've probably heard of this before. The experiment has three components: a screen, a panel with two thin slits cut in it, and a light source or beam of electrons. The resulting experiment determines if the source used acts like a wave or a particle. Imagine shooting a bunch of paintballs at the slits, which act like particles. The resulting pattern on the screen behind would be just a cluster behind each slit. However, if the source is wave-like, the resulting pattern on the screen would be what's known as a diffraction pattern. Imagine what a wave pool looks like. The water rises and falls rhythmically. Now imagine a second wave maker in the same pool. Sometimes the waves will line up, creating bigger waves, and other times they'll clash, canceling each other out. This combining and canceling forms this diffraction pattern, which creates a series of lines across the screen. So to recap, the source hits the slits and creates a pattern on the screen. If the pattern is two clusters, it's particle-like, and if it's a series of lines, it's wave-like. The initial formulation of the experiment was performed by Thomas Young long before quantum physics was even a theory. It was George Thomson and his student Alexander Reid that modified the experiment to put de Broglie's theory to the test. They created a crystal structure which, based on the wavelength of an electron that de Broglie predicted, should cause electrons to act wave-like. When they fired a beam of electrons at the double slits, the result was a series of lines, a diffraction pattern. So yeah, matter can act like a wave or particle based on the circumstances. Already, with the knowledge we've gained so far, we can circle back to the first time I mentioned quantum physics in the lesson on chemistry. In that episode, we discussed how electrons configured themselves in an atom, specifically that there are energy levels. First, remember that each row on the periodic table indicated a different energy level. These levels were discrete, there were no half levels. Sound familiar? If electrons are acting as quantum particles, then they are restricted to discrete energy levels, like light. It was Niels Bohr who put this idea into effect. He used Max Planck's quantum theory to adapt the Rutherford experiment results into a shell-like structure of discrete radii that is still taught today in high school chemistry. And now you know why. Erwin Schrödinger pressed pause on the podcast. Fascinating, he thought to himself, and gently tipped his 1920s cup filled with his 1920s tea and drank it slowly in the year 1920. If electrons have wave-like properties, then they must be predictable by classic wave mechanics, he probably said, and left the room, leaving his earbuds on the bed. Little did he know he was about to change the very reality of physics as we knew it. I mentioned earlier that it's hard to identify one person as the start of quantum physics. And while I still think that's true, if we're giving away a most important contribution to quantum physics award, most, if not all, physicists would probably give the award to Erwin Schrödinger. Schrödinger built on everything we've already discussed and added one thing: statistics. To understand his equation, we need to understand waves, and to do that, we're going to be talking about rope. Rope is a very good way to grasp the concept of waves. Imagine a very long rope that goes as far as you can see. If you took one end of the rope, lifted it up, and created a whip-like motion, that crest will continue to move down the length of the rope. If the rope was perfect, the wave could continue forever. This is a lot like unrestricted light, a source that generates the wave and then propagates until stopped. Now imagine a shorter rope that's anchored to a wall. When you go to whip the rope, the wave reflects off the anchor and travels backwards. Now imagine you continually try to whip the rope. What will happen then? If you try this in real life, it will probably form what's called a standing wave. A standing wave is created by the motion of two waves moving back and forth in equilibrium, which creates nodes, or locations where the rope stays still, and antinodes, or locations where the rope oscillates from extreme to extreme. Standing waves have something called harmonics, which are based on the number of nodes in the standing wave. The first fundamental mode would have 0 nodes, the second one 1 node, the third one 2 nodes, and so on and so forth. Those sound kind of like discrete energy levels. Schrödinger's equation revolves around what's known as a wave function. The wave function is a specific kind of wave that a particle can exist in given the restrictions we put around it. For example, if we put an electron in a box, which is a classic quantum physics problem, the resulting wave function is a standing wave, just like we talked about before. Now, like the rope, the wave can take on a number of configurations based on the number of nodes in the wave. In differential equations, which is the math that is required to use Schrödinger's equation, each of these configurations will be associated with an energy value called an eigenvalue, which essentially means that each solution to the equation has a unique value. Now here comes the hard part. While the wave in the rope example was the physical position of the rope, such that the crest of the wave is the physical height of the rope, that is not the case in quantum physics. The wave for an electron is the probability that the electron is there. So a crest in this wave means that the particle is more likely to be there, not that it actually is there. This is what I meant earlier when I said we are combining statistics with mechanics. The wave function is a probability model for how quantum particles exist if they acted like waves. Now think about this. If there are multiple solutions at different energy levels that only give us probabilities of where the particles are, where the heck is the particle? I introduce superposition. I earlier said that each possible energy state was an eigenvalue, which is all the possible solutions to the equation. Well, a component of that is that the solution is the combination of all possible solutions together. In other words, the particle exists in all possible solutions simultaneously as long as it can remain a wave. This is superposition. The particle has multiple states superimposed on top of one another, and remains that way until it's no longer a wave. Think about it like layering sheets of clear plastic. If we drew a wave on top of each sheet of plastic, each wave representing a different energy level or eigenvalue, then when we layer each sheet on top of one another, we would get all the possible solutions at the same time. This is what superposition is. When we try to measure a quantum particle in such a way that its mass, momentum, position, or velocity become more particle-like, the superposition collapses and we are left with only one wave. and the probability of the particle collapsing on that wave is dictated by Schrödinger's equation. Wait, what? If your brain isn't fried by now, then you've either heard this before or are stronger than me, because this took me forever to understand. For many scientists, this was the nail in the coffin. Quantum physics had to be wrong. Einstein famously said, "God does not play dice," meaning there's no way mechanics can be probabilistic. Niels Bohr said, "Anyone who is not shocked by quantum theory has not understood a single word." And even Schrödinger himself said, "I don't like it, and I'm sorry I ever had anything to do with it." And if you're not on the same page, let's do a couple of thought exercises with quantum physics. Let's imagine a cube room with a singular door. Inside the room, a machine drops a tennis ball at a random place in the room. We are standing outside the room. While we are outside the room, the ball could be anywhere. But when we open the room and see where the ball is, we can deduce where the ball was dropped from. Also, if we close the door, wait a few seconds, and open it again, we can predict where the ball will be. This is conventional physics and conventional logic. Now, if the tennis ball were a quantum particle, no matter where the machine dropped the ball, when we open the door, the ball could be anywhere in the room, since the ball would be in a superposition of all locations in the room. So not only can we not determine where the ball was dropped, if we close the door, wait, and then open it again, the ball can again be anywhere in the room, regardless of where it was before. Now, remember the double slit experiment, that there was one of two patterns created: clusters for particles, dispersions for waves. If we took a beam of electrons and ran the double slit experiment as usual, we would get a dispersion, indicating the wave-like nature of the electron. However, let's say we wanted to figure out exactly how many electrons went through each slit. So we put an electron detector in front of each slit that would count the electrons going through. If we fire the electron beam through these, the wave function for each electron would collapse at the slits, and we would not get a dispersion pattern, but a cluster pattern. Simply by measuring the quantum event, we changed the outcome. Causality, observation, everything is put into question by these theories. Quantum physics is divisive, difficult, unruly, and the bane of every modern physicist. But it works. We don't want it to work, but it does. All right, I think it's time for a long overdue break. When we return, we will discuss the implications of quantum physics and the interpretations that result. And that should do it. With this machine, the many worlds of the multiverse are at my fingertips. Oof. I wonder what different versions of me exist out there. And on. Hey, what's up? You look identical to me. Yeah, I'm you. No, but like, exactly like me, clothes and all. What's the difference between our worlds? I don't know. I turned mine on like a second ago. You must have sneezed or something. You're saying that we're identical except for one sneeze? Then you dropped out of college, moved to Vegas, then moved back from Vegas and started college again. Yep. Well, that's boring. What did you expect? The multiverse is every possible configuration of quantum states, not just a handful of interesting ones connected in some weird web-like structure. Whoa, this is cool. Wait, why do you guys... Let me guess. You went to the bathroom before you turned on the machine. How did you... Yeah, actually, I need to go to the bathroom, too. Hey, why do you look Can it, bathroom and sneeze boy?
What the?
I've been
across the
bounds
bounds
of the dimensions.
What do I have two nickels? How dare you? I'm a smart boy.
Maybe this wasn't a good idea. Welcome back. Before the break, we learned the basics of quantum mechanics, the idea of probability densities, wave functions, and quantized energy. The nature of quantum particles being probabilistic is a problem. Not a physics problem, but a metaphysics problem. Quantum mechanics argues that knowledge about quantum systems is impossible, since the act of measuring them causes the system to change. The rest of physics is built on the simple idea that your observations reflect reality. But quantum mechanics is standing in opposition to that. But we are prepared for this. I have intentionally given multiple lessons on philosophy, metaphysics, and ethics alongside math and physics so that we can discuss this to its fullest extent. So let's look at some of the interpretations of quantum mechanics and what they would mean if they were true. First, let's talk about the easiest one. Shut up and calculate. Yes, this is a real interpretation of quantum mechanics, sometimes referred to as the agnostic theory. Who cares about the nature of causality and measurements and reality? The math works, so don't waste your time. This answer is boring and a cop-out in my opinion. But it often is the first one taught in schools, so your physics teacher doesn't have to be your philosophy teacher. But you'll get no such sympathy from me, so let's move on. The first interesting one is the Copenhagen interpretation, also known as the orthodox position. This view sees quantum physics as everywhere and nowhere at the same time. Before taking a measurement, the particle simply doesn't exist in any of the superposition states, and it was only upon taking a measurement that the particle then existed. In our tennis ball room example, this would mean that when we close the door, the tennis ball does not exist. It is everywhere in the room, and it is nowhere in the room. Then when we open the door, the ball pops into existence as we have taken a measurement. It was this interpretation of quantum mechanics that pushed Schrödinger over the edge. His famous thought experiment of Schrödinger's cat was intended to show how ridiculous quantum mechanics was at describing reality. If you aren't familiar with the experiment, it goes something like this. Radioactive decay is caused in part by the probabilistic nature of electrons in atoms, which is the reason why our lesson on radioactive decay involved probability. The likelihood a particular atom has decayed can be examined by quantum mechanics. If we built a device that housed a radioactive atom that once the atom decayed released a deadly poison, then if we placed the device in a box with a cat and closed the box, something strange would happen. Since the box is closed, we are not taking any measurements, and therefore the atom is in a superposition of having decayed and having not decayed. And since the poison is linked to that decay, the poison is also in a superposition of having released and not released. And since the cat would die if the poison is released, the cat is in a superposition of being alive and dead. This is Schrödinger's cat, and the Copenhagen interpretation of quantum mechanics would say the cat is simultaneously alive and dead until you open the box. The ball is everywhere, but nowhere. I mentioned earlier that Einstein and a few other scientists were vocally against the final form of quantum mechanics. They did not doubt that Schrödinger's equation was correct, but they did doubt that it was complete. This thinking led to what's called the hidden variables theory, or the realist theory. Hidden variable theory states that although we can associate a probability with which state a particle is in, there is something that either we haven't thought of or can't measure that ultimately determines the outcome. For Schrödinger's cat, hidden variable theory would say that the atom will decay in exactly 2 minutes. Why that's the case is something we don't know yet, but that is what will happen. As a result, the cat would be alive until that 2-minute mark and then dead after that. Quantum mechanics can give us insight into the probability that the particle has decided to be in any state, but our measurement doesn't actually change anything. This would allow all of our old assumptions about physics to be true, that observations reflect reality. This theory also solves a problem we haven't posed yet, but one that hidden variable theorists did: quantum entanglement. Having a single quantum particle is already a mechanical mess, and when we involve 2 quantum particles, it only gets worse. Quantum entanglement involves the mixing of quantum particles and the resulting pairs of viable states that can exist when this happens. An example of this is electrons orbiting in atoms. Each electron has something called spin, which can either be spin up or spin down. In atoms, electrons like to pair up with one spin up and one spin down. So, let's imagine we grabbed a pair of electrons and separated them. Then we measured electron A to see if it spin up or spin down. If it spin up, then electron B must be spin down. And if A is spin down, then B is spin up. This is quantum entanglement, and it's what the hidden variable theorists stated is the reason for their theory to be true. If the Copenhagen interpretation is true, then if we pull the electron pair apart, A and B are in a superposition of both states, spin up and spin down. When we measure either A or B, then both wave functions collapse as we know what the other particle is. It's the opposite. This means either information was transmitted to the other electron faster than the speed of light, which would break relativity, or some hidden variable decided the outcome before we removed the pairing. So, which is true? Well, we can actually eliminate 2 of these theories based on the work of J.S. Bell. Assuming that hidden variable was true, Bell created a scenario where entangled particles had more than 2 possible states, but that measuring one would still give us insight onto what the other one was. The result was that hidden variable caused the system to stop agreeing with quantum physics. In other words, if hidden variable theory is correct, then quantum mechanics is wrong. Additionally, this put to bed the agnostic viewpoint, because regardless if hidden variables was right or wrong, we can make determinations on the initial state of quantum particles, and it is necessary to do so to use quantum mechanics. We owe our thanks to the works of Aspect, Granger, and Roger, who experimentally tested Bell's theorem. Their equipment was far more sophisticated, but we can actually do something similar in our own houses. If you grab 3 pairs of polarized sunglasses, you'll have yourself 3 quantum state detectors. Polarized sunglasses are kind of like slits. They only allow light of a particular orientation to pass through. If you take two pairs of glasses and put one at 90 degrees from the other, the result is pitch black. This doesn't come as a surprise, as the first lens would block half the light, allowing only vertical light to pass through, and the second would only allow horizontal light, which blocks the other half. If, however, you place a third lens at a 45-degree angle from the other two and put it between the two lenses, the result is that some light makes it through all three lenses. Hidden variable theory would imply that photons had an initial orientation to begin with. So the result of having an additional measurement change the result goes against what hidden variable theory stands for. Quantum mechanics, though, embraces the idea that measurements change the state of quantum particles, so by taking a third measurement, we have effectively changed reality. Therefore, hidden variable theory is wrong. Quantum mechanics is right. So it seems the Copenhagen interpretation is the last one standing, right? Well, there are hundreds of other theories about quantum physics out there, each with their own interpretation of what happens when we take a measurement. One of the more famous ones you've probably heard of is the many worlds interpretation. In this theory, the wave function never collapses, at least not in the sense of reality as a whole. When you make a measurement, all possible states of the quantum system happen simultaneously in different, unobservable histories. This has been abstracted by science fiction to become the multiverse, the collection of branching timelines that result from all possible outcomes. This poses its own question of the nature of consciousness and free will, which you are free to think about in your own time. Well, this is the end of our long road. My goal this entire time has been to teach anyone quantum physics, beyond just a couple of interesting tidbits. I wanted you to feel as though you could learn quantum physics or any other complex subjects, regardless of what you knew before this podcast. I wanted you to have intuition. So, did I succeed? Do you feel like you not only learned stuff, but know how to learn? I guess I can't ask that question. You're on your own now. Let's see what reality you'll make. If you like what you heard here and want to learn more, the content of this episode comes in part from the textbook Introduction to Quantum Physics by David J. Griffiths and Darrell F. Schroeter, as well as other books and articles which you can find out about in the description. If you would like to view a transcript or want to cite this episode, that information is also in the description. Entuition has been an independent project that I've done on my own. If you would like me to continue this podcast, please share this with your friends and family. Your support is invaluable. That means valuable, by the way.